Hello. So today we are going to talk about a few probability questions, and the ones I'm focusing on in this video are related to combinations. And when you need to use combinations, when you really don't have to use them, and some of the links between problems where you are using combinations. Hopefully will help tie all of this together for you. So in my first example, I have written that if you're selecting only one object in a certain scenario, there is no need to use combinations. So for example, in our first problem, it says a bag contains 4 red, 5 green, and 6 blue marbles. What is the probability of picking a green marble? So since all you're picking is one marble, and you want to know the chance that it's green, we do not need to use combinations. We just need to show that there are 5 green marbles in the bag. So there's 5 different ways to pick a green marble out of, and then in this bag, the total number of marbles is 4 plus 5 plus 6, which adds up to 15. So there's 15 total different marbles that we could pick when we reach in and select one. So the chance of getting a green is 5 out of 15, which reduces to 1/3. The most common wrong answer that I see for this question is as soon as a student reads that there are 5 green marbles in that bag, they, for some reason, think immediately that there's a 1 in 5 chance of getting a green. That just isn't true because there's 5 green marbles in the bag, so that's 5 successes, and there's 15 total marbles. And if you remember, the definition of probability is the number of successes, which is the 5 that are green, and out of the total number of outcomes, which, since there's 15 marbles, that's the denominator for this problem. So that's how you would do a pretty straightforward question where you're just selecting one object. Now, when you move on into a harder question, such as this is when you're selecting more than one object, then you must use combinations. So in my next example, we're using the same bag of marbles, but now we're going to select 3, like we're reaching our hand in and grabbing 3 marbles and pulling them out without looking. What is the probability that 2 of those are blue and 1 is red? Well, we do have to use combinations for this. So for the 2 are blue portion, there are 6 blue marbles, and we want to choose 2 of them. 6C2. C actually stands for combination, but kind of a little slang that you can use to have it make more sense to you is choose. C, think of C as standing for choose. So there's 6 blue, and we're choosing 2 of them. But that's not all. We want 1 of them to be red. So we look back, there were 4 that were red. So we're going to multiply 4 out of 4 red, we're going to choose 1. And then the denominator is the total of all outcomes that could happen, which we know from before there's 15 marbles in this bag, and we're going to choose any 3. So that's our denominator. The reason we multiply is because we're doing this and this. We're choosing blue, certain amount of blue, and a certain amount of red to create the 3 marbles that we're picking. And is the key word to multiply. So this would give us our answer. So I just punched this into the calculator and I got 12 out of 91 as the probability. Now, on our next page, we continue talking about combinations. And my point here is that when you're using combinations, you also must create the entire outcome in the fraction that you're writing. So what I mean by this, in this example, it says, from a deck of 52 cards, what is the probability of getting 3 aces during a game of 5-card poker, which means you're going to get 5 cards altogether. So here's what I mean about the entire outcome. The question, all it cares about is the probability of you getting 3 aces. But here's the entire outcome. You're still getting 5 cards. So you're going to get 3 aces and any 2 other cards. And that factors into the probability. So that's what I mean about creating the entire outcome. So again, since there's 52 cards and altogether we're selecting 5, we have to use combinations because we're choosing more than one single card. So the number of ways to get the 3 aces, well, in a deck of cards, there's 4 aces altogether, and we just want to choose any 3 of them. So 4C3, or 4 choose 3. But then, to create the entire outcome, now to get any 2 other cards, well, 52 minus the 4 aces leaves you with 48 other cards. And we just want any 2 of those. So to finish out our hand of 5-card poker, out of the other 48 cards, we want to choose any 2 of them. So that is my numerator. And then the denominator is the total of all outcomes that could happen, which means that out of all 52 cards, we could choose any 5 of them. And that gives us our denominator. And it's multiplication again for the same reason, because we're choosing the 3 aces and the any 2 other cards. So and is multiply. And I did this in the calculator and it gave me 0.0017. So we can just say that. And then in this next question, it's just showing you the same idea. It says, in the same scenario, what is the probability of getting all hearts? So if you think through a deck of cards, there's 13 hearts. And out of the 13 hearts, we want to choose any 5, because it said you're going to get all hearts. And then we don't have to multiply by anything else, but just to show you how you would create the entire outcome. There's 13 hearts. And so out of 52 cards, if you subtract 52 minus 13, that means that there's 39 other cards. So if you're getting all hearts, that means out of the 13 hearts, you're going to choose all 5 cards. And out of the other 39 cards, you're going to choose none. And then the bottom is still 52, choose 5. And this 39C0, that is optional because 39C0 is just equal to the number 1 if you punch it into a calculator. So if you would just write 13C5 over 52C5, you really are creating the entire outcome. Even though on the top you only put the part about the hearts. And it's because the other number about the non-hearts just ends up equaling 1. So it's really optional. You don't have to write that portion. So let's see what this answer gives us. So from the calculator, if you punch this in, you end up getting 0.000495. So it's a pretty small probability of getting all hearts in a 5-card hand. And then we have this other formula that you've probably learned about in class, which is the binomial probability formula. And what I'm going to explain here is that when there are exactly 2 outcomes for some situation, like tossing a coin, where you would get either heads or tails, you sometimes need to use binomial probability. So in my first example here, I am explaining that if it's an all or nothing type of question, you really do not have to use the binomial formula. Like in the example, I'm tossing in a coin 10 times. What is the probability that I toss 10 heads? So all 10 being heads. That's the all or nothing. Nothing would be if I said, what is the probability that I toss none of them heads? You really do not need to use the binomial formula. If all 10 are heads, I could think of it like, well, on my first toss, it's a 1/2 chance, 1 and 2. Now I'm tossing it a second time, so it's again a 1/2 chance that it would be a heads. And a third time, and so on, and so on. I'll just write this out, but we could just do it 1/2 to the 10th power. So 6th toss, the 7th, the 8th, the 9th, and the 10th toss. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Perfect. So that's just the same as saying 1/2 to the 10th power. That would be the probability. And this is equivalent to 1 in 1,024. That looks kind of weird, but that's the answer for that. All right, now start a new page here. Let's imagine you're tossing it 10 times. So tossing the coin 10 times, and we want to know what is the probability of getting exactly, let's just say getting exactly 7 heads. Now, this is not an all or nothing anymore. Getting exactly 7 heads, we have to think through the binomial formula. And here's how it would get pieced together. I'm going to show you with this example. In 10 tosses, we want exactly 7 heads. So that would be a 1/2 chance each time of getting heads. So that would be 1/2 to the 7th power. Just like in the previous example, it was 1/2 to the 10th. But we have to create the entire outcome. So if there's 7 heads, that means there would be exactly 3 tails. Now, it's also a 1/2 chance of getting tails, but that wouldn't always be it wouldn't always be 1/2 for both. I'll show you a different scenario where that's not true. But a 1/2 chance of getting tails, and you would get exactly 3 tails. Then there's this other part of the formula, which is a C, a combination, because we don't know which 7 tosses will be the heads, and that does increase the probability by thinking that through. So what we say is, out of the 10 tosses, we're going to choose any 7 of them to be the heads. And this right here is the binomial formula, and this will give you the correct answer. And one other thing to notice, this 10C7, your answer will come out exactly the same if you wrote 10C3, because choosing 7 of the tosses to be heads is exactly the same as choosing 3 of the tosses to be the tails. And you can test it out in your calculator, but 10C7 and 10C3 are exactly equal to each other. So then we can use our calculator to get this final answer. So in the calculator, it ends up being 0.1172 when you round it. And I did the 10C7 and 10C3 in the calculator just to show you. Those both equal the number 120. And just to show you one last thing, instead of tossing in a coin where the chance of getting the 2 outcomes is the same because it's just 1/2 for both, what if we roll a dice 10 times? And we want to know the chance or the probability of rolling exactly 7 sixes. Well, so the chance of rolling a 6 would be 1/6. and the chance of not getting a 6 is the other 5 numbers. So that would be 5, 6. So the way this would get pieced together is almost identical. Out of the 10 rows, you want to choose any 7 of them to come up as a 6. The chance of rolling a 6 is 1/6. So that's to get a 6, and we want exactly 7 of those. The chance of not getting a 6 is 5/6, and we want exactly 3 of those. So this right here would give you the correct answer to this question. And this ends up being 0.000248 when you do it in the calculator. So hopefully this shows you just some of the types of problems where you use combinations and the times when you really don't have to use combinations. And that clears up a little bit of confusion if you had any confusion about these problems.